All right, welcome. Welcome to today's discussion on the Spin-1 system. So this Spin-1 is a type of particle, just like we talked about spin-half particles. We are now going to talk about Spin-1 particles. So this is a particle with three possible values for the measurement of the spin component along any axis. So you could measure spin z to be equal to +1 h bar, or 0 or -1 h bar. So we would have three different, if we write this in the eigenvalue form, there's the +1 state, which would give you +1 h bar for the spin along the z-axis. And then there's the 0 state, and then of course the -1 state. All right, so remember that these are all along the z-axis, and that in its own basis, an operator is diagonal and the eigenvalues are the unit vectors. So what this means is that in the z basis, so in z basis, that SZ is represented by the matrix, the diagonal matrix, with its eigenvalues just down along the diagonal. So +h bar, 0, -h bar go in the diagonal. Then we fill in the rest with the zeros. And we can write the +1 state as represented by the unit vector 1, 0, 0. The 0 state is represented by the unit vector 0, 1, 0. And then the -1 state is represented as the unit vector 0, 0, 1. All right, so I am going to do an example and then we can move on from that. So we are going to look at the example 217. So problem 217. This tells us that we have a spin-1 state that is prepared in a state. So we have a spin-1 particle in the state psi, because that's what we always call our states, which we are representing by the vector 1 over the square root of 30, 1, 2, 5i. So we can quickly check that this is normalized, 1 squared plus 2 squared plus 5 squared. All right, so that's 1 plus 4, that's 5 plus 25. Yep, that's 30. So you take the square root. Yeah, that would be normalization. Part A asks us, what are the possible results of a measurement of SZ, and with what probabilities would they occur, and to calculate the expectation value of the spin component SZ. And then in part B, we're going to calculate the expectation value of the spin component SX. So let's start with part A. The probability of measuring spin Z equal to +h bar is equal to the probability, which I'm going to call +1. And this is the absolute value of the +1 state, its overlap with psi squared, which is equal to 1, 0, 0 times psi, 1 over the square root of 30, 2 over the square root of 30, 5i over the square root of 30. Ran out of room here. So I multiplied these together. The probability of measuring +h bar is going to be then this 1 times 1 over the square root of 30 plus 0 times 2 over the square root of 30 plus 0 times 5i over the square root of 30, quantity squared, or just 1 over the square root of 30 squared, which becomes nice. This is just equal to 1 over 30, which is about 3.3%. Remember, it's nice to write both as the exact fraction, if you can find the exact fraction, include that, but also a percentage here just to help us get a feel for how big it is, since it can be difficult to compare some fractions. So let's look at, so this is the probability of measuring SZ to be plus 1 H bar. Let's now look at the probability of measuring SZ equals 0. SZ equals 0. So the probability of measuring 0 is going to be 0 psi quantity squared. So we'll write this in the bra form, 0, 1, 0. Now remember, it doesn't matter what order I do these this multiplication in, because I'm going to square the results. So naturally I use the unit vector in the bra state because it's easier to convert. So this is 1 over the square root of 30, 1, 2, 5i. When I multiply these together, only the second term comes through, and this becomes 2 over the square root of 30, or 4 over 30, which one can write as 2 over 15, which is approximately equal to 13.3%. All right, let's do our last one, which is SZ. It could possibly also be minus H bar. So the probability of measuring this result is, of course, going to be the -1 bra times the psi ket. And this is 0, 0, 1, 1, so 1 over the square root of 30 times 1, 2, 5i. Of course, only the third term makes it through. So this becomes 5i times the square root of 30. Now, because there's an imaginary component, this becomes 5i times the square root of 30 over the square root of 30 times its complex conjugate, which is minus 5i over the square root of 30. So this leaves me with minus I squared times 25 over 30. And remember, I squared is -1, so the negative ones cancel. I get 25 over 30. 5 goes into this one 5 times, or 5/6, which is approximately 83%. So at this point, we should double check that all of our probabilities add to 100%. So the probability of measuring something should be the probability of +1 plus the probability of 0 plus the probability -1. So this was about 3 plus like 13% plus 83%. So this was what, 16? 6, that's 9, that's 99%. And these were all approximations, so that's probably 0.3 onto everything. So yeah, that would be 100%. So general rejoicing ensues. So we just want to make sure that this makes sense. Let's now find the expectation value for SZ. And this is going to be the value of our measurement times its probability of occurring. So the probability of measuring H bar times so the measurement H bar times its probability, 1 over 30, plus the next measurement, 0 H bar times its probability, 4 over 30, plus negative H bar times its probability, 25 over 30. And here I've just carefully taken the ones that all have the common denominator 30, because I know I need to add them together. This one happily is just 0, for which there is much rejoicing. And I get h bar 1 minus 25 over 30, or minus 24 over 30 h bar, which is equal to minus 4/5 h bar. Oops. There we go. And this is the end of part A. All right, let's move to part B. With the part B, we are going to find the expectation value for Sx. And after running some Stern-Gerlach experiments, what we will find is that the +1 in the x direction is equal to 1/2 times 1 in the z direction, plus 1 over the square root of 2, 0, plus 1/2 -1. Or I can represent this by the vector 1/2, 1 over the square root of 2, 1/2, which can also be written as 1/2, 1 square root of 2, 1, depending on, what makes the math easier. 0 in the x direction is equal to 1 over the square root of 2, 1, minus 1 over the square root of 2, -1. So there's no 0 component in this one, which is represented by the vector 1 over the square root of 2, 1, 0, -1. And then -1 in the x direction is 1/2 times the ket 1, minus 1 over the square root of 2, 0, plus 1/2 -1. Again, I can write this as 1/2, 1 minus the square root of 2, 1. So we can do the same thing for Sy, and we will find that we can write the matrix forms of these operators for Sx as h bar over the square root of 2, and find that this is 0, 1, 0, 1, 0, 1, 0, 1, 0. This way. And that Sy can be represented by the matrix h bar over the square root of 2 of 0, minus I, 0, I, 0, minus I, 0, I, 0. So notice that this one's anti-symmetric. Okay, we're going to find the expectation of Sx in part B. And we're going to use the other method for finding this, which is that this is the state psi times the operator times the state psi. This will also give me the expectation value. You should use whichever form is easier. I used the other one, the measurement times the probability in the first part, because I already had all of those values. There's no need to do another calculation. I don't have any of those values this time, so I'm just gonna go ahead and do one calculation instead of 3. Okay, so I'm gonna write this in the, represent this in matrix form. So I get 1 over the square root of 30. I'm gonna take the bra of psi, which is 1, 2, minus 5i. So I took the complex conjugate. 0, 1, 0, 1, 0, 1, 0, 1, 0, times 1 over the square root of 30 times 1, 2, 5i. Let's do a little bit of rewriting over here. I'm going to get 1 over 30 when the two square root things all multiply together, and I'm going to get an h bar over the square root of 2 from the Sx, which I totally forgot here. Sorry, there should be an h bar over the square root of 2. I tend to forget that a lot, so be careful. And then I'm going to multiply by 1, 2, minus 5i times now my, well, there's the cat. 0, 1, 0, 1, 0, 1, 0, 1, 0 times the column vector 1, 2, 5i. I'm going to start by multiplying the matrix times the vector because I'm more comfortable going that direction. So h bar over 30 square root 2, 1, 2, minus 5i. Here I get 0 times 1, so that's just 0, plus 1 times 2, plus 0. And here I get 1 plus 0 plus 5i. And then I get 0 plus 2 plus 0. Let's go to the next page. So this I can write, this is still expectation of Sx, which is equal to h bar over 30 square root of 2, 1, 2, minus 5i. And I'm going to multiply this by 2, 1 plus 5i, 2. And I'm going to multiply these two vectors together. So this is going to give me h bar over 30 square root of 2. 1 times 2 is 2, plus 2 times 1 plus 5i, minus 5i times 2. Do a little bit more rewriting, h bar over 30 times the square root of 2. And this becomes 2 plus 2 plus 10i minus 10i. We say, oh, thank goodness, we're on the right direction. The imaginary parts cancel, which is a relief. They should. If they don't, we screwed up somewhere. And this becomes 4h bar over 30 square root of 2. So 2 goes into here twice and into here 15 times. And then I can divide out the square root of 2 and put it up top. So this becomes the square root of 2 h bar over 15. So Sx, the expected value, is going to be the square root of 2 over 15 h bar, which is approximately 0.094 h bar. Because I don't know about you, but the square root of 2 over 15 doesn't mean very much to me. But certainly having an approximate decimal helps me understand where it is. All right, that's the end of problem, I think this was 217, but nobody remembers. And I will see you all in class.